Assalamu alaikum ji. Let us move to another scenario when the capacitor is charged. In the previous case we saw that the capacitor is initially uncharged, and while it is initially uncharged the voltage across the capacitor is 0 at time t is equal to 0. But for the sake of analysis and progressing in the topic, let us assume that there was some charge on the capacitor, that is at time t less than 0, that is before the operation of the switch, before the closure of the switch. The capacitor was charged to some voltage V naught, right? So it can be said that at time t is equal to 0, which is the time of the closure of the switch, and slightly less than the time t is equal to 0, I have designated it as t is equal to 0 minus, and in a similar way at time t is equal to 0 plus, that is an instant right after the closure of switch, the voltage across the capacitor is V naught. Since I already told you that the capacitor does not allow an instantaneous change in its voltage, so at time t is equal to 0 plus, the initial charge of the capacitor will be there and there will be no extra charge right at the instant of the closure of the switch, which will be added to the capacitor's initial charge, right? So at time t is equal to 0 minus, or t is equal to 0, or t is equal to 0 plus, all these instances are very much close to each other. We can say that the voltage at the capacitor is V naught. So again, referring to the solution of the differential equation, V of t is equal to k1 plus k2 times exponential of minus t over tau, we derived that k1 was equal to Vs, the source voltage. So at time t is equal to 0, we can write V naught in place of V of t and Vs in place of k1, that is obvious. And at time t is equal to 0, the exponential term will be equal to 1, because the exponential of 0 is equal to 1, and we will be left with only k2. So the equation comes out to be V naught is equal to Vs plus k2, or k2 is equal to V naught minus Vs. So the overall solution of the equation will become, since it is equal to k1 plus k2 times exponential of minus t over tau, so V of t will become k1, which is Vs, k2, which is now equal to V naught minus Vs, times exponential of minus t over Rc, since tau was also equal to Rc, which we derived in the previous section. So let us now solve an example. This is, you are having a linear circuit in front of you. You have a voltage source which is connected to a resistance R1, which is in turn connected to a resistance R2, and a combination of C1 and C2 through a node which I have defined as a red dot, so that you can see that this node is the point of interconnection of R1, R2 and the combination of C1 and C2. Anyhow, the voltage of this node is designated to be as V of t. Now this circuit is almost similar to the circuit that we derived in the previous example, that we solved in the previous example. It was having just one resistance and one capacitance. This is having two resistances and two capacitances. So in this case, what we need to do is, first we need to find out the equivalent capacitance. Since the capacitance in series are solved in the manner as resistances are solved in parallel, so C equivalent will be equal to C1 times C2 divided by C1 plus C2. This is also same as 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Anyhow, so C equivalent comes out to be 0.0833 microfarad. Right. Another thing that is related to the discussion that we did above is the initial condition. The initial condition of both the capacitors states that the capacitor C1 is charged at some voltage 5 volts and C2 is charged at some voltage 10 volts. So the total charge on both the capacitors combined is equal to 5 plus 10, that is 15 volts. And V of t can be found out using the voltage division rule. So if you see the voltage across R2, it is equal to R2 divided by R1 plus R2 times Vs. This is VDR, simple voltage division rule is applied. So V of t comes out to be 10 over 40 times Vs. Vs is the source voltage. So now what you need to do is, you have the solution to the differential equation, that is k1 plus k2 times exponential of minus t over tau. You have seen that when you have a capacitor that is initially charged, then the solution is V of t equals V of s plus V naught minus V of s exponential of minus t over RC. So which R and which C are to be used in the solution? The resistance, the capacitance is very simple. The two capacitances are connected in series. You can find the equivalent capacitance, which is 0.0833. What about resistances? So basically, if you go back to the course of electrical circuits, you should remember the Thevenin's theorem. The Thevenin equivalent was very much similar to the simple RC network that we did in our previous example. There was a source, there was one resistance, and there was one capacitance. So capacitance can be treated as the load. The voltage and the resistance are simple, the Thevenin equivalent voltage and Thevenin equivalent resistance. So you can find out the Thevenin equivalent resistance by simply replacing the voltage source by a short circuit. I have drawn the circuit in red, and if you see the resistance, the resistance from the points A, B, it is actually the parallel combination of R1 and R2. So R Thevenin is equal to R1 R2 times R1 into R2 divided by R1 plus R2, which comes out to be 7.5 kilovolts. And at last, you can have your Thevenin equivalent with the Thevenin resistance and the equivalent capacitance RT and CEQ. The time constant is equal to Thevenin resistance times equivalent capacitance, which comes out to be 1 over 1600 seconds. Just use these values in the above equation. V of t is equal to Vs plus V naught minus Vs times exponential of minus t over RC. You'll have your solution. V of t is equal to Vs plus 15, that is the total potential available before the closure of the switch, before the operation of the switch, and exponential of minus t over RC. Replace RC with 1 over 1600 and it comes out to be minus 1600 t. Right? So this is how you solve a first order circuit with multiple resistances or capacitances. What you need to do is find the equivalent capacitance, find the Thevenin resistance, and put the values in the equation. That's it. Thank you.